We're going to talk about the models of the atom. There are three models you should be aware of. Most of what you see in this video today should be review from chemistry. The first model we need to talk about is the Rutherford model. So this is the gold foil experiment. Rutherford bombarded thin gold foil with alpha particles. Right? Remember, alpha particles are positively charged particles. What he found was that instead of slowing down or even stopping, the alpha particles went right through that gold foil and were deflected or scattered. So here's a quick diagram of what Rutherford did. You have that gold foil in the middle, you have a fluorescent screen behind it to detect the alpha particles in their path that they're traveling, and then you have the actual device that's shooting the alpha particles. And here's what he found. Right? You can see those arrows, those lines represent the path of the alpha particles. Most of the alpha particles went straight through that gold foil and onto the fluorescent screen. And what he found was that most of the particles were not deflected. They just simply went straight through. Their path was unchanged. However, some of them did deflect. Okay, so most of the particles passed through without being deflected at all. A small number were scattered at different angles up to 180 degrees. So 180 degrees means it's just coming back straight at the device that was shooting the alpha particle in the first place. So there were three things that happened here. The first is that deflection. So some of the alpha particles were deflected, and the reason they were deflected is because, remember again, alpha particles are positive. If they're deflected in a certain direction, that means they're coming close to another positively charged particle and they're being repelled away. So this comes back down to Coulomb forces. Remember Coulomb's law? We're talking about charged particles and how positive charges interact with other positive charges in this case. The second thing they saw happen was the rebound, right? So it could just rebound directly and come back to where it came from, right? And then the third thing is just pass straight through, nothing happens. So those were the three different things that Rutherford found. Okay. And the big thing is that from this experiment, Rutherford concluded that the atom is mostly empty space, but it has this small, dense, positive core. Right? And he knew it was positive because those alpha particles were deflected, meaning they came too close to the positive nucleus and it was repelled away. The other thing he found is that it had electrons orbiting in a planet-like path far from the nucleus. So you get a diagram that looks something like this, right? This is kind of your planetary model of the atom where you have the nucleus as the center and you have electrons that orbit around. Okay, most of the atom is empty space. That's your key with the Rutherford model. The other thing to just kind of take note of here is the ratio of the size of the radius of the nucleus and the size of the radius of the atom as a whole. So the ratio between these two is between 1 in 10,000 and 1 in 100,000. Right? So that just kind of shows you the radius of the nucleus versus the radius of the whole atom. So the atom is mostly empty space itself. Okay. A couple problems with the Rutherford model. So in the Rutherford model, you have these electrons that are in orbit, kind of in a circular path. And we know that anything that travels in a circle is constantly accelerating. And if electrons are accelerating, they should constantly emit energy and spiral down into the nucleus. But that doesn't happen. So there's problem number one with this model. The second problem with the Rutherford model is that it does not explain the spectral lines. Okay, I know in chemistry you did a lab where you were observing the different spectra of atoms. Okay, and this has to do with the energy associated with each atom, energy of those electrons. You get very specific spectral lines in specific places, and they're also specific colors. And this Rutherford model cannot explain that. So that's where the Bohr model comes into play. So you also need to know the Bohr model. Right? In the Bohr model, you have very specific energy levels around that positive nucleus. Okay, so here's the Bohr model. This is a similar diagram. Hopefully this is what pops into mind, right? You still have that positive dense nucleus in the middle. Here it's a little green circle. And then you have electrons that are found in very specific rings around the nucleus, right? And so those rings were labeled n equals 1, n equals 2, 3, and 4. The key to remember here is that the ground state is the level that's closest to the nucleus, and that's where the energy of the electron is the lowest. So it has the least amount of energy in the ground state. So when electrons come and fall down into the nucleus, that means they're losing energy. Okay? As an electron jumps to the next level, it gains energy. And the Bohr model does help us explain those spectral lines and those specific amounts of energy associated with jumping from one ring to the other. Okay. So this is a diagram that's on your reference table, and this goes right off of how an electron can jump from one ring to another. This specifically, it says at the bottom here, is the energy levels for the hydrogen atom. Okay. This is on your reference table. Your reference table also gives you the energy levels for mercury, I believe. So these are different for each different atom because each different atom has a different amount of energy associated with moving from one ring to the other. Okay, and so you'll notice on the left-hand side here you have n equals, this is your energy level ring. So n equals 1, this is the ground state closest to the nucleus. And then you have n equals 2, that's this line here, n equals 3, so on and so forth. Each level has a specific amount of energy associated with it. Now you'll notice way up at the top here on the right-hand side, this is the unit for energy, EV, electron volts. This is a unit that we used when we talked about circuits, right, towards the end of that unit. So you may want to go back and look at that, right? This is an electron volt. There is a conversion for you on the front of your reference table. So just keep that in mind. So these values represent the energy associated with each level. So in the n equals 1 level, you'll notice you have an energy of negative 13.6. The negative sign indicates to you how much energy you're missing in order to go up, right? So this electron in the ground state needs to absorb 13.6 electron volts in order to ionize. So in order to go all the way up to 0, right, you'd have to add 13.6 electron volts to this electron because it has essentially negative 13.6 electron volts of energy. So each level has a specific energy associated with it, and to jump from one level to another, you have to absorb a very specific amount of energy. Right? And so you can find that specific amount by just subtracting between two levels. So if you want to jump from n equals 1 to n equals 2, you have to absorb a certain amount of energy. So you're just going to subtract those two numbers and see how much energy is needed for an electron to go from n equals 1 to n equals 2. And again, it's very specific for each specific atom. Again, this is hydrogen, and that's where those spectral lines come from. So the Bohr model explains these atomic spectra. As an electron jumps to higher energy level, it can only absorb specific energies. Thus, it's only absorbing specific frequencies of light. And remember, the frequency of a light wave tells you the color. The absorption spectra shows which colors are absorbed into that, essentially that atom, right? And so you're going to get black lines, so something like this. So this is the absorption spectrum for hydrogen. And you can start to see those energy level diagrams. So here would be your n equals 1 or your n equals 2, and then the next specific amount of energy, right? The next level, how much energy you're absorbing to move up energy levels. The emission spectrum is created when electrons fall down. So when an electron releases energy, it's going to emit a photon, a particle of light, and that is, again, going to have very specific spectra. So you are going to see the color instead of seeing the black line, right? So when it emits that electron, it's emitting a frequency, and again, frequency is associated with light. Now, if you place these two side by side, you'll notice that each of those lines fall in the same spot, and that has to do with the fact that for hydrogen, the change in one level to another, the amount of energy required is very specific, and it always remains the same for that atom. Okay, so the key here is that these are always the same for the same element, but they're different for different elements. So this is the emission spectra for hydrogen. The emission spectrum for neon would be different. Right? And that's how you were able to do that lab in chemistry. You had to identify which element you were looking at based on the emission or the absorption spectrum you were seeing. Okay, so again, if I put these two side by side, you can see that the lines, right, in my absorption spectrum, the black lines, and my emission spectrum, the colored lines, they're in exactly the same position because that's a very specific amount of energy that's being absorbed or emitted based on the levels where you'll find electrons in a hydrogen atom. Okay, so that's the Bohr model. Right? This is how you identify each element. The other model of the atom you need to be aware of is the cloud model. So this is the model that we know and use today. However, we use the Bohr model as a visual. Right? So we kind of use a combination here. So the cloud model of the atom comes from Schrodinger. Right? And so Schrodinger used some of the wave properties with looking at the models of the atom, right? And so he knows that matter waves are probability waves, and you can't know the exact position for an electron, but instead you know the probable position where you'd find an electron. Okay, so the highest probabilities where you're going to find electrons correspond to those Bohr rings and those energy levels. So if you were to look at a cloud model of an atom, you'd see a high probability of finding an electron that falls at these very specific rings around the nucleus. Right, so we're kind of using a combination of these two models. Right? There is not a specific orbit for an electron. Instead, it's just a region where you will most likely find an electron, and we call that an energy state. Right? So we call it a state, not a specific level, and it's called a state, and when it's in that state, it has a specific amount of energy associated with it. Now, one thing to note is that a state can hold no more than 2 electrons, and the area where you have the highest probability of finding an electron is called the electron cloud, right? The cloud model. So this is essentially what we're dealing with. So you can see this little red dot kind of flashing all over the screen. In the center, you have a positive nucleus, right? Here's my positive nucleus. And then this little red dot that's flashing all over the screen is the path of that electron, right? So it's found here, over there, over there. It just kind of moves randomly. And if you were to plot the position of that electron, you would see these kind of faint dots that you see around here. Okay? And so if you plot this over a period of time, you can see that there forms like a dense ring here. So it falls along this ring location around the nucleus the most number of times, right? It comes in very close to the nucleus a very few number of times, but this is the highest probability of where you would find that electron. And that's essentially what the cloud model is, right? Really, it's a mathematical model. It's very hard to visualize. So what we do is we use the Bohr model, that solar system model, as kind of our visual representation, but we know that each of those rings around the Bohr model represents the highest probability of where you would find an electron.